Welcome back to ECE 441A, 541A. Homework number 6, if you haven't been reading your emails, has been shifted. It's now due on Wednesday, the 9th. And there's additional material on not only the which root locus diagram, but also arrival and departure angles. And so you might want to take a look at that for one of your homework problems that's due on Wednesday now and not today. There is no class on Friday, and homework number 7 hasn't been assigned because I don't want you trying it without having seen anything in class on it. Today we are going to start Chapter 10 material, which is on design using the root locus, and that's what homework number 7 will be covering. Those two topics, root locus construction and root locus design, will be the contents of exam number 3, and the structure of exam number 3 is a little different than what you've seen before. It's now 9 problems, but they're more breaking down the steps that you might have to do in a root locus sketch, meaning now you don't have to sketch a complete root locus diagram and get 0 points. Now you can sort of build on different aspects of the root locus and hopefully get pieces of the root locus constructed and get points based that way. And it's not just each problem builds on the other. It may be completely different types of rules for the root locus construction in each of those problems. Lab number 3 is dealing with designing controllers that are now output feedback based. It's not full state feedback. In lab number 2, you were able to assume that you were measuring the position and the velocity, scaling those individually, and putting those in as the input. Now in lab number 3, we're only assuming we have the position signal available, and we have to now filter that or control that to make the system behave the way that we might prefer it behaves. And the project in 541, we have the 3 deliverables, and the first deliverable is tell me what you're going to do, and the last 2, the second one is really the main one, that's the report, and the third deliverable is your reflective paragraph. And several of those due dates are on the 7th of December, which I'm sure you're already counting since you have senioritis. That's the last day of class. In terms of root locus examples, you could look at table 9.3, and speaking of table 9.3, if I can find what happened there. So if you look at transfer function 14 in table 9.3, this is similar to problem 714 in the homework, where it's conditionally stable, which means that the root locus is venturing over into the right half plane, then it sneaks back into the left half plane, then it goes back into the right half plane. You are trying to find these points, these values of gain k, where you are in the left half plane, when you're in the right half plane, etc., so that you can bound k or know which range of k might lead to a stable system. In this particular diagram, you have 3 poles to the right of 2 zeros. Those those squares, maybe they're not green, but those squares are the squares where you might have closed loop poles. And in this particular case, they've selected the gain k to get you into the left half plane of those conditionally stable poles that are bouncing back and forth between left half plane and right half plane. And that's what they're meaning by conditionally stable. If the gain is not right, if it's not the Goldilocks value, you may be unstable. And you're trying to now find that range in one of your homework problems. In this particular case, if we've now marked K1 as the gain to get us to that frequency, and K sub 2 gets us to a higher frequency in terms of where those 2 poles cross, they're coming in conjugate pairs, and K sub 3 is the last one, which range of k, so now I have 4 different k's. I have a k without a subscript, that's the adjustable gain. I have k1, k2, and k3. I want you to tell me what value of unsubscripted k would produce a stable system response in this example. Can you tell me? So now you want it to be greater than k2 and less than k sub 3. Is that true? That gives you a section of the root locus that's in the left half plane. Is there any other region of k on this adjustable gain k that might produce a stable response? Pardon? So now so k1 is going to be k1 both for j omega sub 1, j omega 1, and minus j omega 1. So k1, what is our k unsubscripted is starting with k equals 0. That's at these poles, which means that k going from 0 all the way up to k1 is still stable. Then between k1 and k2, we go into the right half plane and we become unstable. In this particular case, then, sorry, don't pay attention to me. I'm just talking, trying to, and I thought I wasn't hearing myself, so that gets a little bit scary when you're talking to yourself and listening for your talking, but let's go on. So stable is that range of k, and the first response on my question for stability said that we wanted k to live between k sub 2 and k sub 3. And now, for unstable, if we now have a k value that's bigger than k1 and less than k sub 2, then we are in this particular piece and we're unstable. We're not only there, but we're down here. Everything happens in a mirror image. These are in complex conjugate pairs. And finally, we have if k is bigger than k sub 3, we're unstable. Is that clear? And that's really what you're trying to determine in one of your homework problems is where are we crossing this imaginary axis in, and when are we going to actually be stable with the appropriate range of k? What are we doing when we march up this imaginary axis? If we were evaluating our transfer function along that imaginary axis, I don't know if you remember me walking in 320, but I would pretend to walk up the j omega axis. That's the Bode plot. You're evaluating g, or g of s, h of s, with s equal to j omega. Meaning you could use MATLAB to sketch the Bode plot with just a command BODE and the system in parentheses, and now you try to find what frequencies is that transfer function equaling minus 180 degrees. That's what's happening at these particular transition points. And that might be helpful in problem 714. And in particular, that was system number 14, G14, in the textbook table 9.3. So there's some other tools that you could use. You could even use a zoom command in MATLAB to try to expand the picture and the graphical image, and that allows you now to maybe more finely determine with root locus find particular values of k on your root locus diagram. What I want to do today actually is get into controller design, which is really what we just did, we were finding a gain K that produced stable responses, and that's a controller design. But what we want to do today is build a little bit beyond maybe just a controller which is just a gain, and maybe sprinkle in some poles and zeros. And to start, we're not going to go crazy. We're just going to pick 1 0 and 1 pole and sprinkle those on the S-plane to try to dramatically change our root locus shape. This is the system configuration, and what we want to do now is probably in most of this class we will have h of s equal to 1. We simply have negative unity output feedback, but what we are concentrating on now is designing this compensator g sub c of s to change our behavior, whether that's transient performance or steady state accuracy. We may have a combination, and that's what the PID controller will allow us to do, is actually influence transient behavior and steady state accuracy, because it plops a pole at the origin. It has an I term, it has an integrator term, and we've learned that that helps us with steady state accuracy. But it also can make our transient performance a little less desirable, and that's why we have the P and the D term, the proportional and derivative terms, in our PID controller. Let's look at an example of how we can create a controller, G sub C of S, to change the dynamic behavior of a system. And this particular system is a simplification of what you have in the lab. Now we've basically removed the spring, and all we have is damping. So you could think of a mass moving in syrup or heavy oil, something, and it's a little bit sluggish in terms of its behavior, but we don't have a spring in there. And I'm hoping that with this particular system you remember how to write the equations of motion. Do you? You'll need to by the final. And it's always nice to have this in mind as you go through these problems. What could this system, what could this G of S actually represent? But in this case, we have an applied force U, and now that's opposed by our inertial force caused by the mass, M, and it's opposed by this damping force due to the dash pod. Or we now have U of T, that's our applied force, is now equal to M x double prime, that's the inertial force, plus the damping force. That's our time domain equation for the dynamic behavior of that system. And we can take that into the frequency domain, which is where we like to work, because now we're playing in the S-plane. That's where we're going to be sketching the root locus and putting down maybe some additional poles and zeros. What happens when I Laplace transform this equation and I'm really looking for a transfer function? If I'm looking for a transfer function, do I have to worry about initial conditions? No. So now I can just apply the Laplace transform and how it relates to derivatives. Or I now have U of S is equal to S squared M plus SB times capital X of S, where I've already factored out the appropriate terms and isolated my Laplace transformed position variable. Let's say this is now the output that I want in my transfer function, which is position, and let's say that this is now my input, which in this physical picture is our applied force. I can now find my transfer function by looking at the ratio of x over u. And that's now 1 over s times sm plus b. And if you look at that, if that wasn't an m and a b, this could actually look like a generic DC motor. So not only is this coming maybe from a mechanical system, it could also be arising from an electromechanical system, a DC motor. This transfer function then is fairly generic or general. You could say this is also the structure of a DC motor. Just to make things maybe a little easier, suppose that we say that our mass is 1 and our dash pod has a value of 1. The numerical values now for m and b, we're forcing those to be 1, and g of s now is this system that has a pole at the origin and a pole at -1. Again, that could be this mechanical system, it could be a DC motor, or maybe a normalized DC motor, and that's the system that we are living with. Now, suppose somebody gives us the following design specifications. And suppose the design specifications require that we have a settling time of 1 second and a percent overshoot less than 20%. And we can now think of those in terms of somewhere in our complex S-plane. What's a 1% settling time give us? So here is our S-plane, and if I say settling time, what do you see? Okay, now we're seeing hypotenuse, we're seeing root loci. Now if I say settling time, what do you start imagining mentally? Yes, I see somebody doing this. So now it's a vertical line, isn't it? But that vertical line is basically somewhere located, usually in the left half plane, to give us a particular speed of response for settling time. We can find where that vertical line is, knowing that our 2% settling time is 4 tau, or 4 over sigma, and we wanted that to be less than 1. That was our specification. That's what somebody's requesting happen. And now we can say, oh, we now want our sigma, which is the magnitude of our distance into the left half plane. We want our sigma to be bigger than 4. Here is now our sigma value. And we want to be somewhere over here. But what about our percent overshoot? What do you see when I say percent overshoot? If you're thinking about food, and people were already thinking about cookies this morning, now I'm thinking a pie or pizza wedge. That's now what we're seeing for percent overshoot. It's this angle. We want to be maybe within a particular angle, and for a percent overshoot, less than 20%, we could look at our table or our figure. Is it 5? I forget the number now, which figure that is, but this corresponds to a zeta value of about 0.45. And we could do the inverse cosine of that and find that theta now at 0.45 is 63 degrees, and we want for less than 20%, we need our theta to be less than 63 degrees. Which now says that I can go over here and try to sketch a 63-degree angle, which I know needs to be bigger than 45 degrees. So let me go up here and go completely into my writing from before, and I could just keep going. But now we want this angle that we found from our percent overshoot. We need to be inside this large wedge that's bounded by a 63-degree angle. And we can take the intersection of that sigma value and 63 degrees and say I want to end up with my dominant poles in the intersection of this vertical line and this angular line. And it's maybe hard to see because I'm getting into my wording on my design specs. But we don't want our imaginary part to be so big that it's making our dominant poles have an angle bigger than 63 degrees. That's the idea. Let's look at the system that we started with, which is 1 over s times s plus 1, and see if the closed loop poles, just using a gain k, will put us in the shaded region. We're wanting our closed loop poles to end up in the shaded region. What's the root locus of g of s look like? And now you should actually be almost instantly sketching that mentally. But if we are not, what's my pole zero excess? 2. So now do I have some interesting asymptotes? When I say interesting, I'm meaning something other than 180. 180 is sort of boring. That's going off to minus infinity. But in this case, we do have 2 asymptotes. Their fundamental angle is defined by 180 divided by the pole zero excess. And we can now say that we want to iterate through little l up to p minus z minus 1, which in this case is 2 minus 1, or up to 1. So we have l equal to 0 and 1 for our angles. This is now 180 degrees over 2, or 90. Our angles now of our asymptotes are at plus and minus 90 degrees. And the centroid of those asymptotes, we add up our poles. We have a pole at 0 and we have a pole at minus 1. We subtract the zeros, which we do not have any, and then we divide that sum, or algebraic result, by the pole zero excess. And in this particular case, that's really all we have to do in terms of sketching the root locus. We can now go up here and we can say here is a pole at the origin, a pole at minus 1. You know from rule number 2 which piece of the bread is on the root locus. Have to keep using food here. It's between 0 and minus 1. That gives us an odd number of poles and zeros to the right of that segment. We simply have 2 isolated poles, nothing else. Those 2 go together, and they break away where? Exactly between them, since there's no other poles and zeros present. They are going to go together symmetrically. And we just computed the centroid of our asymptote to be at minus 1/2, which is in fact the breakaway. And in this case, we now break away at minus 1/2. One pole goes up, one pole goes down, and there is our potential closed-loop poles if we just had a controller that was a gain. If we just had a controller that was a pure gain K and we adjusted K from 0 to infinity, these are the possible closed-loop poles that we would have available on the red. Does the red go through the desired region from our design specifications? No. So we can't achieve the design specs with just a pure gain controller. And that's what we hopefully just made clear. Here we found that what is possible with pure gain adjustment is not going to get us what we want in terms of our design specifications. In this first step, or the original root locus, we were selecting a value of K and not including or introducing any controller poles or zeros. I.e., our controller was as simple, this G sub C of S was just a gain K. Just for fun, why don't we say, let's just see how we could adjust that gain. If somebody said, I want a gain, give me a gain. So now we're in the stadium and somebody says, give me a gain. And you go, K. What's its value? I don't know. But you can find that K if somebody specifies a location. And where's a location going to be? It has to be on those red lines, the root locus. So let's say that somebody tells us, suppose we let S sub delta equal, we know the real part is minus 1/2 if the gain is cranked up enough. We could be at minus 1/4 and minus 3/4 for a given K. But now we're cranking up the gain K to at least get us to the breakaway point. And let's just go ahead and make it a little bit more interesting. Let's say that we now crank up the gain to get us to closed loop poles at minus 1/2 plus and minus J2, which in our diagram says that we are now wanting to locate our closed loop poles at those two locations, where I'm assuming that. Now, how do we adjust K? How do we find the K to get us to those triangles? Does everyone understand what we are trying to do? We're adjusting the gain K from between 0 and infinity. Now we could just continue to crank up the gain K and still remain stable. But what happens as you crank up the gain K a lot? Do you change the settling time? If you crank up the gain a lot, K, does that change your settling time? What impacts the settling time? Sigma. Do you change sigma if you crank up the gain K? Sigma's stuck at 1/2, isn't it? So you're not going to change the settling time. What are you changing? You're changing omega sub d, aren't you? Which impacts how quick you get up there, the response, omega sub d, and the omega sub d sigma ratio gives you theta. So now you would be ringing a lot if you cranked up the gain K a lot. Your frequency would be much higher, but your settling time would still be the same. How big would that be? 4 tau. Well, tau is 1 over sigma. 4 over 1/2, 8. So now you have an 8-second settling time, really no matter what you do with k, as long as you get k to a value that gets you to the minus 1/2, minus 1/2. We can now actually use one of the conditions that we've been playing with, and that's the magnitude condition and the phase condition. We can use the magnitude condition to find k. And that says if we're living on the root locus, the magnitude of kg of s is equal to 1. Because we know the denominator is governed by 1 plus kg of s equal to 0. We solve that for kg of s, and we have the magnitude and angle. Here, we have now k over s plus 1. That's the kg of s equal to 1. That now says that k, if we keep k positive, is s, the magnitude of s, and the magnitude of s plus 1, and we want to evaluate that at s equal to s, well, I'll call s delta, which is minus 1/2 plus j2. We could evaluate it at minus 1/2 minus j2, but we'll get the same answer. Let's go positive. Let's be positive this morning. Start the week off right. Which means what? Now we simply replace s with minus 1/2 plus j2 in that formula, and we now have minus 1/2 plus j2. We want to find that magnitude, and now we multiply that by the magnitude of s plus 1, which is minus 1/2 plus j2 plus 1. And in fact, those are just the hypotenuse of these right triangles. If you look at this particular sketch, the value inside the magnitude of s is going 1/2 in the horizontal direction and 2 in the vertical direction to actually achieve, then, I don't know what color to pick. I'm really getting confused just by color selection. But I'm trying to find that length, that hypotenuse. That's L1. And the other one, since it's, in this case, just 2 poles, it's exactly the same. I go 1/2 in horizontal and 2 in the vertical. Again, I'm looking at that same hypotenuse length, which in this case ends up being 1/2 squared plus 2 squared. Since I have the real part squared plus the imaginary part squared, square rooted and multiplied together, I'm just now getting rid of the square root in the square and saying, oh, inside one of those is x squared plus y squared equaling c squared, which I'm not sure I can say that in Korean, but it's kind of cute in Korean. So this is now what? 1/4 plus 4, or 4 1/4, right? $4.25 for K. Not a bad price. And what have you got? What have you found? Now you have a controller that gets you to closed loop poles at minus 1/2 plus and minus J2. A G sub C of S equaling 4.25 yields closed loop poles at S delta equal minus 1/2 plus and minus J2. And as we just earlier had determined, our settling time is not really what we wanted. Our 2% settling time is 4 time constants, which is 4 over sigma. That's 4 over 1/2, which is now the 8 seconds. And you could find the angle. You could go to your figure and find what the percent overshoot would be for those two triangles in your closed loop pole or in your closed loop system. Yes? So the question was, why are we doing the magnitude condition and not just setting the denominator equal to 0? We are setting the denominator equal to 0. Really, the magnitude condition is derived from this formula, and we solve that, and we have kg of s equal to -1. We are trying, k is right now unknown, and we're trying to find a way to determine it. We know all of g of s. The only thing that we don't know in this magnitude formula is our gain k. And we can now solve that given a particular value for s. We know exactly where those closed loop poles are living because we drew the root locus. That's the power of the root locus. And this now tells us we have no hope of getting inside the shaded region, which is determining our design determined by our design specifications. We now need to dramatically change that original root locus shape or pattern. And now the question is, how can we satisfy the original design specs? Well, we obviously have to really bend that root locus from what we have right now. So we need to drastically change or modify the original root locus, and one way to do that is by using what we will now refer to in the rest of the semester as a phase lead controller. So if I now talk about a phase lead controller, you will know exactly what I'm talking about, and you will know that that's meant to dramatically change the original shape of your root locus. In this case, our phase lead controller is not that complicated. It's just one zero factor, one pole factor, and a gain. We have three parameters, z, p, and k. But to make it a phase lead, we want the zero to be closer to the origin than the pole. And if we simply sketch this controller's pole zero diagram in the S-plane, then what we have is we have a zero here and a pole here. There's minus z, which is the zero location, and here's minus p. That's the relationship between our pole and zero in a phase lead controller. If I say phase lead, you immediately should start seeing this configuration of poles and zeros. We now have a zero shaker and a pole shaker, and we're putting those on the S diagram to hopefully modify the original root locus. Now, in our case, what do we have? We had a system that ideally we wanted to be beyond that vertical line at -4 and not too big in terms of our vertical dimension or imaginary part. But let me change the color of that -4. This is now -4. There's -1. We had a pole here and we had another pole there. How could we change the shape of this root locus with that particular configuration of pole and zero? Did everyone follow that? That's exactly what we need to do. So let me try to rephrase, not change the wording at all, but just try to restate what was said because you maybe didn't hear it. The easy thing would be to cancel. Let me do our controller in red. Let's cancel that pole, the open loop pole, and now the point was put a pole somewhere to the left to allow our root locus poles to eventually get to the left or at -4. And what do we know about a two-pole behavior's root locus? It's easy to sketch, isn't it? They come together and they break away at the exact midpoint and then they leave. And where they break away is halfway between the two poles. So if we want that halfway between to be to the left of -4, we now know where our other pole of the controller needs to be located. To make it easy, why don't we make that pole over here at -10? So that now we have a root locus that looks more like that. Let me write down what we've done. We actually just said let z equal, that looks like a t, so let me change that. Let z equal 1, or now our controller 0 is at s equal -1, and that now canceled the open loop pole at s equal -1. Now, let me say something that I hope everyone wakes up right now and hears this. Is everybody awake? We can cancel poles and zeros, but we can't do the following. We never, ever, ever want to cancel poles or zeros on the imaginary axis or in the right half plane. We can cancel what we want in the left half plane, but don't be canceling in the right half plane or on the imaginary axis. That will give us unfavorable behavior between maybe the disturbance input and the output. It will be unstable. So let me try to make that as clear and dramatic as possible. Never cancel a pole or zero on the imaginary axis, the j omega axis, or in the right half plane. Oh. So if you want to miss 50 points on a 10-point problem, do that. Okay? Don't do that. Now, that said, that does not mean that you can't put poles and zeros in the right half plane. You can. Sometimes we have to put an unstable pole in an unstable system to actually create a stable system. Two negatives do make a positive sometimes. We may have to do that, but we cannot cancel a pole or zero by a choice of pole and zero in the right half plane. We can place poles and zeros in the right half plane. We just can't use them to cancel other poles and zeros. Is that clear? That's a distinction that I want you to make. And in our case, we wanted a breakaway Now we're talking about where do we place our controller pole. We wanted a breakaway to the left of s equal -4. And that said that then our pole had to have a p-value of 8 or more. And we actually decided, just to make the math a little bit cleaner, we went ahead and said, let's let p equal 10. So that now g sub c of s, we have 2 of the 3 parameters already picked. We have the 0 picked, that gives us this s plus 1 factor. We have our pole picked, that gives us the s plus 10. Now we need to pick the k. But this is very similar to how we found K before. It's just we have a different collection of poles and zeros. Really, we don't have a zero now because it's canceling a pole. What we have is we have this combination of controller and plant, which is now K, S plus 1 over S plus 10 times 1 over S, S plus 1. And now those two factors cancel, and we effectively have a 1 over S times S plus 10. And I think you can see that the breakaway point, or the centroid of our asymptotes, is now minus 10, minus 0, minus 1, minus a minus 1. The minus 1s have canceled. We really didn't have to keep track of those, but I'm being very explicit. We have now 3 poles and 1 0. This is now minus 10 over 2, or the minus 5 that we already found. And to find K, I say, give me a K. And now somebody says 9.8. I'm not sure where they came up with that, but let's see if we can find it. So, how do we find a K? From the magnitude, but how do we determine K? What do we need before we can find a K? We're going to find K using the magnitude condition, right? We need to find S delta, right? Closed loop poles. I say, give me a K. You go, give me an S sub D, or an S sub delta, right? And I go, oh. Where do we put S delta? We know it's this if we crank up the gain big enough, right? What would be a nice value? What are we learning is nice in this class? Maybe. Well, if we haven't yet, we will start learning that this 45-degree angle is sweet. That's 45 degrees. It's a theta of 45. It's a zeta of 0.7. It's a percent overshoot of 5. It gives you a nice speed. It gives you very little overshoot. That's just a nice value, having that 45-degree angle. So we are now looking at that for our S deltas. And given that, we can use the magnitude condition to say now we have K, S plus 1, S plus 10 times 1 over S, S plus 1. I really don't need to be carrying those around, but I am, equaling 1. And now we have K equal to S, S plus 10, and we want to now evaluate that at a new S delta. Do I want to put a party hat on him to make him different from the S delta before? This is now minus 5 plus J5. But you now know how that's going to look. That's now minus 5 plus J5. We have minus 5 plus J5 plus 10. Or we now have that duplication inside the magnitudes of our arguments. We really have 5 plus J5 squared. Or 5 squared plus real part squared plus imaginary part squared. There's 2 quarters, we're at 50. Or now we have our controller. Our G sub C of S is now 50, S plus 1 over S plus 10. And now if somebody said, give me a G sub C, you would say, what are my design specs? And I would say, here's your design specs. And you would go, thank you. Then you would say what? Let me sketch where I need, where my desired region is in the complex S-plane, and I will find root locus branches inside that desired region by an appropriate choice of zero, pole, and gain. And we've now designed a phase lead controller. Isn't that exciting? Go team. And we're out of time, right on cue. So we'll pick up at that point on Wednesday.